Okay, so we'll get that going. And this is going to cooperate with me. It did. This is here, and we can start. So what I want to do is I want to go over, and I think I'm going to take an explicit case in that continuity equation derivation. We can do the x, y, or z momentum, pick one, and we'll go through and do it explicitly. So do you want to do x momentum, y momentum, or z momentum for the derivation? Okay. I heard y, so we're doing y. Okay. So what I want to do is I want to look again. Yeah, at this guy here. Oops. And just one thing, give me our fancy new notation for this. How else can I write this? T.
Oh no.
T mu nu. Comma. Nu. You know, this doesn't happen with chalk. You know, when you chalk, it just always chalks. Chalk never leaks on you. That's one of the properties of chalk. It just never leaks. And when chalk is gone, it just makes the chalk cut. That's what chalk does. Again, showing the superiority of chalk. Okay. A little nervous. Okay. So this would be our this equals 0. Okay. Morning, Meadow. So what we want to do is we want to look at specific case. And Ryan said the y one. So let's look at the y momentum. Look at y case. So in this case, mu is going to equal 2, like this. So we want to look at basically the case of 2 here. So let's say here's basically some region in space here. Some macroscopic region. And I want to find the total y momentum here. So let's find the total y momentum. For you who are just joining us, it turns out my pen is leaking today. So if you're wondering why I'm going like this periodically, because my pen is leaking. Okay, it leaked again. Okay, so tell me how you're going to write this. Okay, we want the total y momentum. Okay, how do we do that? There's like a little region here. What's the volume of that guy? dV, we're going to write it as d3r, but your dV is completely correct. So this would be your dV. Now, where is our y momentum density? If you look at T mu nu here. Okay, where is the y momentum density? Okay, first column. Okay, right here. It would be the T20 here. This is y momentum density. So tell me how to write then the total y momentum in here. What would you do?
Integrate T30 over D3R.
So T20, Dasser density times. So it's leaked again. So you're gonna take this guy, and we multiply it by D3R. So that's how much Y momentum we have in that little guy here there. And then we have to integrate it over the entire region. That. Does that make sense? Okay, now let's assume that this Y momentum is leaving the surface here. How do I write the rate of change of the Y momentum on here? Where do we have our Y momentum flux? Thank you. Okay, and keep this guy here. Put it over there for the bomb disposal unit. Okay, so where does everything else go? Where's our momentum flux? Y momentum flux. Can you see that, Mandela, the blue?
Not very well. It's just
Okay.
the focus on the computer is a little bit off today.
It is?
It's a little bit blurry, or it could be my internet connection. I can see most things fine. But
Okay.
if you could write a little bit bigger.
Let me try to do something here,
It's not terrible though. Just a little bit.
but hopefully we can actually maybe improve it. So let me do something here.
Oh, I think that got a little bit better.
It could go better, or is it
What?
good as it is now, or no?
Yeah, I think it's good now. I got yeah.
Okay.
I think so. Cool.
I try to write it regardless.
Cool. The blue is still a bit dim though.
Well,
The blue is still a bit dim though.
okay, that's fine. It's not as thick as this one here. I'll go back to this guy here. And just have some entertainment for that. Okay. So where's our flux? Where's our Y momentum flux here?
Zero 3. 0 3.
We're in this matrix here.
Or 0 0 2, I guess. Not sure.
But this guy, and this guy. This right here is our flux. This is flux of Y momentum. Okay, so this is going to be, and again, what does it mean to be flux of Y momentum? It's the Y momentum per area per time. Okay. So what is this? This is the Y momentum flowing out of the X, Y momentum flowing out of the Y, and then, then Y momentum flowing out of the Z. So if I come over to here, I can draw a little patch of area here. This right here is my dA vector like this. Okay. I guess normally I'll leave it like that. I think we normally write it as a lowercase. So I want to know how much Y momentum is flowing out through that region there. So normally what do you do for flux? Normally with flux, what do? You take V dot dA, where V is a generic vector. How are we going to do that for here? So normally, let's put this over here. So normally, flux is written as this some vector v dot dA, right? Through the whole outer surface here, and this would really be this VI DAI. That makes sense? Because this dA vector is going to have a component going the X direction, Y direction, and Z direction, right? This is really your dA xi hat. Plus DAY j hat plus DAZ k hat. Okay. So I know the corresponding thing here written in terms of T. So how would I write it for this guy right here? I'm going to take care of this dot product thing.
We take care of the dot product when we apply the divergence.
No, we're going to use a divergence term after we get the dot product. So I want the analog of this guy here. Okay, in terms of this. So what do I have to do?
Write it in terms of like an upper and lower index.
Well, how would I write it in terms of the T stuff? Well, the T20 is a density one. So this is our density one.
For our
Here.
flux.
Okay, we want the flux.
Oh,
Yeah. So you're gonna take this guy here, this flux here, times this dotted into here. So if I do, I don't want to leak it then. So if I do T21 dA1 plus T, so this is what? This is the rate of change of Y momentum, because I've taken the flux times dA. This is the rate of change of the Y momentum through the along the x-axis, along the x area of this guy. If I take this in times T22 dA2, this is how much Y momentum is flowing out through the dA side of this one here, the dAy side. Then if I do T23 dA3, that's how much of the Y momentum is flowing out of this one here. Because I take that flux times this little area. It's kind of the analog of this flux here. It's a little bit different, but it's just so idea. Okay. Now, what's a nice compact way of writing this?
T2I DAI.
Exactly. T2I DAI. Why didn't I say T2 mu dA mu? Yeah, because the I here I'm using a Latin index. I'm summing on the 1, 2, 3. In other words, X1C. So that's just for that. That's how much Y momentum is flowing out through that little tiny patch there. If I want the total Y momentum flowing out through that whole surface, what do you have to do? No, not yet. Along this entire surface here. So if I want the total, so your total Y momentum flowing out of the surface. I'm going to do this right here. T2I DAI. Now, how am I going to relate it to this? This is your total amount of Y momentum. This is how much that Y momentum is changing with time. So what does this have to equal then? How do I relate this term to this term? Right? This is your total, the change of the total Y momentum unit time. That's what that side is. So what do we have to do with that? It has to equal the rate of change of this with respect to time. Because this is your total Y momentum. Okay. So you can take that total Y momentum here. Right. This right here is your total Y momentum. Okay, and that has to equal, for that entire surface there, that has to equal how much is then flowing out through the side. Okay. Now, why do I have to put a minus sign in there? Yeah, this is decreasing with time, okay? But this is gonna be intrinsically positive. So to make the two sides equal, then I'm gonna have to put this minus sign here. So what do I do with this derivative here? Take it inside here, making it a partial. Now, what do I then do with this side here? Now apply the divergence theorem. How do I write that? It's a triple integral. And how do I generalize this to this thing? Again, what is this guy? This guy is this partial bx, respect to x, this partial by, respect to y, partial bz, respect to z. So generalize it now to this right here.
So the partial
T, 2i,
only partial,
respect to
not one.
XI.
xi, exactly. And we have a sum here. So when I is 1, it's this term. When I is 2, it's this term. When I is 3, it's this term here. Okay, D3R. Now, what did we assume about the region we're integrating over? It's arbitrary. Therefore, the integrands have to be the same. Okay, so I can take this to the other side. We're a natural unit, so it's a more compact way to write this. No. Okay, let's say new. T, 2, no. Equals 0. Now, how would this differ if we were doing the x component? We have a 1 here. The z component, a 3. If we weren't doing momentum, but instead doing energy, what would we then have? No.
The 0.
That'd be this. So in general, what we have is this. T mu nu equals 0. That's what Hilbert forgot to take into account. I told you that Hilbert was right on Einstein's tail with general relativity. He did not account for that. Einstein did. That's why they're called the Einstein equations, and they're not called the Hilbert equations. Questions with that? You're going to get a lot of mileage out of this here. That's going to be really important for us. Okay, so this is where your first test is going to stop. So the first test stops here. And your first test is tomorrow. No, it's going to be next week. It's going to be Thursday next week. I'll send out some little review sheet. But you've had enough of my test. You know how my things go. Okay. Questions? Okay, now we can actually get to what the course is about. Okay, now, okay, we needed this and the other stuff. So I mean, we needed all that information. But we can actually now start getting into real, actual, what is general relativity. And so we have to start talking about curve space and stuff like this. And this is going to take a little while. So it's going to take a couple of weeks to set it all up. So any questions with this? Okay, so this is actually interesting. That
Yes.
somehow it's coming up here and it's going up like that. So I think it actually is coming up from the base too, somehow. Oh, wow, chalk doesn't do that. Crazy. Okay, so what do we have here? So we're going to start talking about curve space. Curve spaces. So first of all, let's go back to flat space. Okay, we're just going to take Euclidean. Uh-oh. Meaning we're only going to be dealing with X, Y, Z. Let's not put in time right away. So if here's my flat space here, here's Z, here's Y, and here's X. What I can do is I can have a point here. This is some point. And I can have a neighboring point. And I can talk about the distance between these two. So this is my distance here. I'm going to set the distance between these 2 points. The distance between these points is, let's call it ds, I'll call it squared. So I should say the distance squared. Okay, so this right here is my ds squared. If you want delta s squared, that's fine, and then take the limit, it doesn't matter. Okay, well, what is this going to be in Euclidean space?
dx dy dz.
Yeah, it's just going to be dx squared plus dy squared plus dz squared. Nothing really too fancy. Now, how can I write this in a little more fancy notation? If I wanted to, I could actually write this as eta ij dxi dxj. Where this eta ij is a matrix. And again, I'm not putting in any time in this. It's just 1, 0, 0, 0, 1, 0, 0, 0, 1. Does that make sense? Because what this is here, this is really dx1 times dx1, because our x1 equals x. This one over here, this is x2 equals y. So this is dx2 here. And this one here, this is x3 equals z. And this is just our dx3 dx3. So I can generically write it like that.
So eta ij,
Is this guy right here?
is that like the identity?
In this case here, it looks like the identity, but it's not the identity. Okay. This right here, we call them the flat space metric. Or just a Euclidean metric. Now, do you have to use X, Y, and Z when you're dealing with flat space? You've all had Calc 3. What else could you do? You could do spherical coordinates. You could do polar coordinate, or the whole thing would be cylindrical coordinates. You could do those. Okay. Now, how would you then write the corresponding ds squared in terms of spherical coordinates? So let's repeat this whole calculation. Well, now let's just figure out how we would do it in spherical coordinates. So we can also describe that space in other coordinate systems. Okay, e.g. a spherical, which we're going to do, or a cylindrical. Okay. So let's do this. So how do you do this? First of all, what are spherical coordinates? And where do we measure them from? Okay, math majors. Okay, a person who had a whole bunch of math as well. R, theta, and phi. Okay, so R goes this way. What is it? What's the bounds on R?
Zero to infinity.
0 to infinity. Okay, how does a physicist always measure theta? Not a mathematician, but a physicist.
You know, I must say, Dr. Laux, both Dr. Kendall and Dr. Cartland have switched to the mathematician way of doing it and have convinced a lot of us. So,
Well, it turns out they're wrong. Okay, that's, I guess we know where they're going to end up in eternity, in physics hell. That's where, because they're doing it wrong. Okay, we're going to do it correctly here. Because first of all, if you take any books and stuff in physics, they're all done this way. And
that's fair.
okay, so good people always measure the angle where? This way. This is theta. Okay. Where does theta go from? 0 to pi. Then phi? Where? Yeah, so we look at the projection on the xy plane here, and this goes here. This is our phi.
Wait, that's how they do it too.
Okay, then they're fine. They're not going to hell then.
I think what they do is in 2 dimensions, they keep phi as that angle. You know what I mean?
Okay, that's fine. I don't have a problem with that.
To keep it consistent, that's what they do. That's the difference.
As long as they measure theta from the z-axis, that's the big one.
Absolutely.
That's always fine. So that's what we have. Now, how do you then get a distance here? I'm going to write ds squared.
Is it like r squared sine theta and then all of the dr, d theta, d phi?
That's how you do the volume element. So the volume element, the d3r, is the r squared sine of theta, d theta, d phi, dr. That's the volume element. I want a little segment. I want some little segment of space. So I want to be here, and I want to be here, and I want some little. So I want this to be the ds squared. Well, it's going to be a lot like what you do in Cartesian coordinates, just tweaked a little bit. Let's look at a tiny little length. If we vary r, keeping the other two variables fixed, and then do it for the other variables. So let's set up some intermediate pictures here. Okay, so let's do this guy. So let's keep theta and phi fixed. Okay, so if we keep theta and phi fixed here, if we're here, then we go this way. So we go this distance. This is my dr. Does that make sense? If I write it as a vector here, this would be like dr in the r hat direction. Okay, so that's what we have here. Okay, now so that would be our distance here. In this case here, the ds would just be dr. Now let's keep r fixed, phi fixed, and just vary theta. So keep R and phi fixed. So how does that look? Yeah, we move over to here. We go like this. This is my d theta. And so this ds in this case is what? R d theta. Does that make sense? Oh, it's just airplane. Okay. Now, let's do the same thing keeping R and theta fixed, but now varying phi. So this is R. Here's my theta. This right here is R sin theta. So this is my R sin theta. And here's my phi. So what does this one look like?
Okay.
I'm going to come over to here. Here's this arc length. This is in the XY plane. This little angle here is d phi. So what's this little arc length here?
R sin theta d phi.
Exactly. R sin theta d phi. Now these are all perpendicular to one another. That ds, this ds, and this ds, they're all mutually perpendicular together. If you put them together, knowing that they're mutually perpendicular, what would then be the ds squared? You have to square these each, because these are all mutually perpendicular. So if I want that total distance, I'm going to have to take this dr squared, add it to that friend over there, or d theta squared. Add it to this one squared. And I'd write it like this. ds squared equals dr squared plus r squared d theta squared plus r squared sin squared of theta d phi squared. What is my eta in this case? And I'm not going to call it eta anymore. I'm going to call it g. So I'm going to write this as as gij dxi dxj. Well, what do you think x1 is going to be? And so your x1 is going to be r, your x2 is going to be theta, and your x3 is going to be phi. And it's arbitrary which one you call these. So in a case like that, what does my G matrix look like?
Still zeros everywhere.
So what's the first element? 1. What's the second element?
R.
Yeah.
Oh yeah. Yeah.
Or squared sine theta. And zeros everywhere else. Now notice, this looks funny, but is this still for flat space? Yeah, this is still flat space. It's just expressed in different coordinates. So this is what we want to do, because this kind of sets up the idea. Oh, hey, I think we need a daily homework 6. Repeat this for cylindrical coordinates. And I want you to write this guy for cylindrical coordinates. and then give me the matrix. Okay. So here's kind of the moral lesson of what we're going to do here. It does not matter which coordinates we use. So what we want to do is we basically want to have equations set up in such a way that I can transform from one coordinate to the next without having any problems. So what we need to do, we need to use to express our equations. In such a way, such a manner that we can transform from one coordinate system to another. The Lorentz transformations are a specialized version of this. Right? Therefore, going from a stationary frame to a moving frame. That's a special case. This is completely general. You don't even have to be moving. Just we're going to use different coordinate systems. So this is going to be called a general coordinate transformation. So in general relativity, so in curved space, in curved spaces, we need to consider general coordinate transformations. Okay, so in other words, i.e. Transforming from xi to xi prime. And so the prime here is going to be, it's no longer a frame moving at constant, the moving frame. This just means a different coordinate system. So this right here, this might be x, y, z. This is r theta phi. And the prime now means a different coordinate system. Does that make sense? And so we're going to have to set up our equations to do this. And that's going to be hard. Okay, now this is all fine here. This is flat space. Now I want to do a case. Let's set this up instead if we have actually curved space. So let's consider. Let's repeat this calculation for ds squared, but on a curved surface. Okay, we're gonna beat this problem to death because this is one of the few that we can do without too much pain. What do you think that crazy curved surface is going to be? What? Surface of a sphere, exactly. So let's consider the surface of a sphere. Actually, once we find out what curvature is and stuff like this, it's one of the few times I'm going to be able to talk about art at Alfred, not poke them and make a little fun of them. We have a beautiful piece of negative curvature on campus. Anyone know what it is? Sure is. I think it's called the wave. So
yeah, it's that sculpture.
Yeah, that turns out to be. I'm so glad that's there. It's a perfect example of negative curvature. It actually is aesthetically appealing on some level. But So if you're introducing people to campus, you can say, and there's our negative curvature. And they'll look at you like, good, I'm glad. Okay, so but let's do this now. Okay, so here's your sphere like this. So you live on this surface here. So the radius of this guy, I'm going to call capital R because it's fixed. So what would be your coordinates on here? Would you use X and Y coordinates? You can, but it's really, really painful. And I'm going to show you actually how to do this, not today, but later on. We're going to talk about embedding something here. You can use X and Y coordinates in here, Cartesian coordinates, but it turns out to be really, really painful to do. Okay. What are the natural coordinates for the system? Spherical. And in particular, which part? Only the. Which variables do I need to specify this?
Theta and phi.
Theta and phi. That's what we use. So this is really a two-dimensional surface. Okay. So we're not, when we write our G for this, it's not going to be a 3 by 3 because our ds squared is not going to be just a 2 by 2. Okay. So let's actually go through and do this. And I'll give you a hint where you know exactly how to do this. So I'm right here. This is theta. Yeah, that's exactly what we get. So what do we get in this case here? We can get this distance here, right? This is keeping phi fixed. So what is this guy here? Yeah, this is just that R d theta. So that'd be the ds here. What would we then do? This guy is capital R sine theta. So that's this guy. So then I can do this guy here. And look at that little angle here, d phi. So what is this little guy? And this is just our R sine theta, d phi. And this is a ds. So in this case here, if I were a ds squared on this, what would it be? Capital R squared d theta squared. Yeah. Okay, so this is just our. Now you could say, well, wait, we're kind of cheating here because this is basically what we got before. No, it isn't. What did we have before? We had a dr squared, and the r was a variable. This right here, when we actually go through and work this out, we're going to find out that this has positive curvature. When we actually go through and work this out. But we can still write the G for this. So the ds squared, the total is going to be what? As in terms of this. Tell me how to write the Gij. R squared, 0, 0. R squared, that's there. Okay. So what we're going to start doing is dealing with basically the separation distance between 2 points in curved spaces. Now, we may have to make another little change in this too. What have we omitted in all this? We have not accounted for time. So when you actually go to general relativity, this ds squared is in space-time. And so what we're going to have to do is, so in general relativity. Yeah, we're going to have this ds squared. This will be in flat space. Flat space-time. We're going to have this guy, this eta mu nu, dx mu, dx nu. And what is the eta mu nu for flat space-time? Almost.
-1 at the corner.
Yeah, the time one comes into that minus sign. So this guy is this. Does that make sense? In general, we have ds squared is going to be what?
Negative d tau squared.
Okay, mu nu. We're gonna, in general, we're gonna go to this guy here. Dx mu, dx mu. And this is gonna be our space-time metric. In a flat space, our G becomes this. So what we'll do tomorrow, we're gonna generalize what kind of spaces we're going to. We're gonna be working with something called a manifold. And I'll explain the conditions for a manifold. And then I want to start setting up basically what it means to be a contravariant vector and a covariant vector. And this is going to be a transformation under a general coordinate transformation. And this is where it's going to start getting really kind of funky pretty fast when we set this up. And you're going to find out some weird things here. We're going to find out that if you try to define a derivative on a curved surface, it gets weird. You're not going to be able to. You're going to have to do something weird on the curved surface to define a derivative. Okay? You can, but not with this. There are elements to it that come in. Okay? All right, this makes sense? Good, okay. Have a good day. Is everything making sense with this? Good.